Hello grade 12s and welcome to another video from the answer series. This is video number 3 in the chapter Work, Energy and Power. In the previous video we saw how the direction of the force vector affects whether the work done is positive or negative. In this video we will practice calculating work done by individual forces. Here are some things to keep in mind when trying to solve these problems. After you've read through the problem carefully, draw a sketch, preferably a free body diagram to show all the forces with their tails at the center of the diagram. We are always after the angle between the two vectors. Now be careful, it's not the angle of the inclined plane. Instead, we're either interested in the displacement vector and the force vector going in the same direction with an angle of 0 degrees between them, or going in the opposite direction with an angle of 180 degrees between them, or sometimes an acute angle between the two vectors. Obviously, if the vectors are at 90 degrees to each other, there is no work done. Once you know that angle theta, we take the cosine of that theta, multiply by delta x and the force magnitude to get the work done. In this first worked example, we can see that we've got a 5 kilogram suitcase being carried in 3 different sort of situations. One's just standing waiting, the other one is being carried horizontally, and in the third one, up a flight of stairs. The force applied on that object is straight upwards, and we're going to work with the force in that direction. In that first situation, there's no displacement and therefore no work is done. In the second one, the applied force is perpendicular to delta x, and so therefore the work done equals 0 because cos 90 is equal to 0. Going up the flight of stairs, we need to be able to see the geometry of the situation a little bit better. We have a triangle with an angle alpha here. The hypotenuse is 5 meters. The opposite side is 1,5 meters. And so we can find out the sine of alpha. Opposite over hypotenuse, rearranged, gives us an angle of 17,46 degrees. But have a look at that angle in this diagram. If I draw a dotted line across here, here's alpha, and you can see that alpha plus theta, in this case, equal 90 degrees. So to get theta, simply subtract alpha from 90 degrees, and that gives us the angle theta. Theta is now substituted into the work equation, and we use the magnitude of the applied force, which in this particular case happens to be the same size as the gravitational force because of the constant velocity. Substitute that in, multiplied by delta x, and out comes a value for work. In example 2, a woman pushes her baby in a pram for 1 kilometer. Again, think about the force vectors acting on this pram. Gravitational force is downwards. A larger normal force is upwards because the applied force is also acting downwards. And then there's a frictional force backwards. There's the force diagram with the delta x shown. We have to do a conversion. 1 kilometer is 1,000 meters. And so now we start to work out the work done by the friction. The frictional force itself is 30 newtons. The magnitude goes in there. The delta x is 1,000 meters. That goes in there. The angle between these two vectors is 180 degrees because they're going in opposite directions. And so out comes an answer of minus 30,000 joules. To calculate the work done by the applied force, let's first work with a component in the horizontal direction. Because the pram is moving at a constant velocity, we know that F net equals 0. So if we take to the right as positive with the friction being negative, then the applied force in the x direction is going to be minus F is 30 newtons. Once more, substitution, firstly of that 30 newtons and of the 1,000 meters, gives us 30,000 joules, because now these two vectors are going in the same direction, and so theta is equal to 0 degrees. Now that we have the horizontal component as 30 newtons, we can calculate the magnitude of the final force. Either use the work equation and substitute in the work done and the 1,000 meters at that angle to give us the size of the force, or simply use the ratio FA in the x direction divided by FA is equal to cos 335, and in that way find out F of A is equal to 33,1 newtons. In the next couple of slides are 3 questions for you to try yourself. The first question is 2 boxes tied with an elastic string on a horizontal plane. Note particularly that they are traveling at constant velocity. You know what that means. In the end, we want to know the work done by the frictional force on that back box. In this question, on an inclined plane, we have a truck freewheeling. What's important here is that the driver is keeping his foot on a brake, and so therefore we have a applied force acting backwards on the truck during that motion. In the end, we will calculate the work done by the brakes over that distance of 20 meters. Finally, a problem in the vertical plane. A rocket is launched. It's held back for 2 seconds to allow enough force to develop. We have to explain where that force comes from, and then find out how much work is done by the rocket motor over the first 100 meters. Pause the video now and try those questions yourself before looking at the answers. Sometimes you might find it useful to work out the net force from a vector sum of the forces acting on an object in a particular direction. Let's have a look at the answers now. After the definitions, we can have a look at the forces acting on that front block. There's of course gravitational force downwards and the normal force holding it up. Applied force that moves it to the right, opposed by a frictional force, and a tension. To get the work done by each of those forces, substitute the force into the work equation to get answers. The applied force does positive work, 240 joules. The frictional force does negative work. To get the tension, use a vector sum of forces, substitute the correct numbers in, and you get a tension to the left as expected. Substitute that number in to the work equation with the 2 vectors going in the opposite direction, and out comes a negative quantity of work. The gravitational force and the normal force do not do any work in this situation. We know that the objects were moving at a constant velocity, which means that we've got 0 net force acting on it. It's quite useful to also write in the unit, 0 newtons. The external examiners like that. Again, we have an opportunity to do a vector sum of the forces, which gives us the magnitude of the frictional force. It's negative because of the direction that's been chosen. We now substitute that into the work equation, and we get a negative quantity of work being done by the frictional force. With the truck on the slope, we are asked first to get components. To get the parallel component, we use sine of theta, where theta is the angle of 12 degrees of the slope here. To get the perpendicular component, we use cos of theta, and so we get the two components that way. Note that in this case, we are using the angle of the slope to get components for the gravitational force. Now we can work on getting the magnitude of the frictional force. The perpendicular component and the normal force are equal in magnitude, and so therefore we can substitute the gravitational component perpendicular to the slope multiplied by the coefficient of friction to obtain a value for the frictional force. Once more, we turn to a vector sum, and we are able to work out the applied force up the slope. It's a negative value because we've taken down the slope as positive. Lastly, substitute that applied force magnitude into the work equation, multiplied by the 20 meters of distance, two vectors going in opposite directions, and out comes a negative amount of work done by the applied force. With the rocket, during those first 2 seconds, there's no work. We can explain the force on the rocket using Newton's third law, because we've got the mass of gases coming out of the back of the rocket, and they are pushing the rocket upwards, while the rocket is pushing that mass of gas downwards. On the rocket itself, if we look at the two forces acting upon it, there's the gravitational force downwards and a larger applied force going upwards. Hence, the acceleration in the upward direction to give us the total force. We once more do a vector sum and are able to get a value for the magnitude of the applied force upwards. We then substitute that number into the work equation. Both vectors are in the same direction, so theta is 0, and we get a positive amount of work done.
If you found this video useful, give it a like and subscribe to our channel so you don't miss any new episodes. Follow us on Instagram or Facebook to stay on top of the latest TAS news and launches. So that's it for now from The Answer Series, your key to exam success.